Welcome to the Jet Propulsion Laboratory, a NASA facility here in Southern California that specializes in the robotic exploration of space and of the Earth. I'm Marina Jurica here with a very small model of NISAE, an Earth-observing satellite that is being put together here right on a lab. And today we're going to be breaking down NISAE, which stands for NASA ISRO Synthetic Aperture Radar. And ISRO is the Indian Space Research Organization that we are collaborating with on this global mission. Now, before we get to the science, we're going to talk about the assembly of this next level spacecraft. And we're going to be talking to two mission experts as they explain NASA is going to be launching the largest reflector antenna ever into space. First up will be payload manager Wendy Edelstein, and then we're going to be talking about the communication system on board and why that is so unique to NISAE with systems engineer Richa Siroki. Welcome, Wendy. Thanks so much for being here today.
Thank you for having me.
So what is NISAE and how will it see the environmental problems differently?
So NISAE is one of NASA's, I would call, a flagship Earth science mission. While most NASA science missions are very focused on a single measurement objective, NISAE is a bit unique. It covers a wide range of science goals, really focused on addressing climate change and our response to disasters and managing those disasters. For instance, I would say that you could look at NISAE as like a Swiss Army knife of radar missions, of science missions. And what I mean by that is that it's looking at many different things in a variety of different ways. For instance, we have measurements that can look at surface change of the climate and surface change of the Earth. So that's used for measuring things like earthquakes, landslides, flooding events, volcanic activity. These are things that we see every day in the news. We're measuring those on a daily basis globally, day after day. We also are measuring and monitoring the melting of our glaciers and our ice sheets, and that's really important for measuring and monitoring the sea level rise, and that's extremely important to our coastal communities. We have our farmers are going to be using the NISAE data as a way to manage their crops and really manage the water usage, because of course water is a scarce resource. So we have a multitude of scientists all looking for different measurements of ways to use the NISAE measurements to really solve everyday problems.
I bet they can hardly wait.
Yeah, they're very excited.
So this model is very small compared to what it actually is. Give people some reference and talk a little bit about the two radars and what sets them apart on NISAE.
Right, so let me first explain what the two systems are. So NISAE is a dual frequency radar system. It's a synthetic aperture radar, which is just a fancy way of saying high resolution mapping radar. So that's what we mean by a synthetic aperture radar. So we call those the LSAR and the SR. LSAR is provided by NASA JPL, and the SR is a radar, an independent radar provided by the Indian Space Research Organization. LSAR operates at L-band, so that's what the L is. And L-band is a long wavelength microwave frequency, which is used to basically can penetrate through the foliage and trees and get right down to the tree trunks and measure carbon. It measures really well with using a repeat pass interferometry, a technique to measure small centimeter level surface change on the Earth. So it's really used to monitor these features, these large scale features. The S-band radar is operated at a little bit higher frequency, and so what that means is it looks at foliage, it looks at vegetation and crops, and that's its primary objective. Let me tell you a little bit about where they all fit on this structure. So NISAE is somewhat unique because it's very large, and this model doesn't do it justice. So what you see here is the entire satellite. In the back here is the conventional satellite components. You've got your solar arrays and the spacecraft bus that does all the commanding and controlling of the spacecraft and the mission. But out here in front, this large piece, that's the actual radar instrument structure, and that houses the L-band radar and the S-band radar, and this is very large. It's about the size of a school bus, so it's very large. You can see some of the electronics are on the outside, and the inside is stuffed full of more electronics, so it's very complicated. Up here you can see the feeds that really are used to communicate and illuminate this large reflector antenna. This is the interface between the Earth and our system, and it basically is used to transmit and receive our radio frequencies from the ground and get them into the system where they can do onboard or data processing. So altogether, this is a very complex system. The antenna is like 12 meters, so that's 40-ish feet, and that's like the size of, as tall as a 3-story building.
Wow.
So everything is very large. The boom is 9 meters, so everything here is very large, and we'll show you some deployment videos to see how that comes together. Because one of the key challenges here is that since this is very large, it has to deploy, it has to be stowed to fit into our launch vehicle. You cannot launch it like this. It'd be simpler, but it can't be done. So we have to package it down very small. And so you can see in this video that the boom here is made up of 4 separate segments. It takes, each segment of the boom is deployed separately. It's wrapping around the structure, as you see, and then it deploys the 4th boom right there, and then the last step is that we release the antenna structure, the reflector structure. The reflector is a composite, there's a perimeter truss that basically opens like a baby gate and has a very lightweight mesh material, fabric material that makes up this material, makes it very lightweight. So the whole antenna only weighs about 180 pounds. So it's a package very small to wrap around this system and launch in a smaller launch vehicle.
And it takes a few days for this process to happen, you mentioned.
Right, so it takes like the first 9 days of the mission. We're going to be going every day we'll deploy a different hinge, and we do it very systematically, but it takes about 9 days to deploy all of the antenna components in the first week of a mission.
Well, like I said to you before, Wendy, we've got to use this technology to make electric pop-up tents. I would really like that. Make camping a little more enjoyable.
Yeah, that's right.
Well, you're joining us for the NISAE live stream with Wendy Edelstein. And so if you have any comments or questions, please pop them in the box and we will get to them a little later in the program. So Wendy, tell me exactly what a payload manager is.
Okay, so I have been with the project for about 7 years, and the payload manager is pretty much responsible for everything you see here, the instrument, the components, the antenna. I have to make sure it gets designed, built, tested, integrated with the other elements, and ultimately I'm responsible to make sure it works on orbit. Part of my job, a big part of my job, is working really closely with the our Indian counterparts, because we have a very integrated system. I had mentioned the S-band system is buried inside here. It takes a lot of engineering to ensure that all these different systems work together as designed and that we can do joint mission operations. So it's a challenging job. Next year I'll be spending a lot of my time in India to do the final phase of testing to integrate the spacecraft.
Very exciting. And we're going to take a look at our next steps video here showing what's going on in our clean room over the last couple of days as it gets ready for testing. So walk us through this, Wendy.
Yeah, so it's exciting. So where you see it right here is the model here is fully deployed. This is what it looks like in a stowed position. This is how we're going to launch it. You can see the various components. You can see people standing around there to get a real sense of size of how big this system is. There's the antenna reflectors being stowed. You can see some of the electronics on the outside of the system. Those golden black things are thermal blankets that keep the temperature nice and warm and comfortable on orbit. So we just finished building it up, and you can see us putting it into a transportation fixture container. And our next step is to basically take that system as is and take it to our environmental test facility and start our next phase of testing.
And that's very important. Tell us a little bit about this next test phase.
Right, so up until now we've done what we call ambient testing. We do it in the clean room, we make sure things functionally work, but what's really important, it has to withstand the environment. So we go up to our environmental test facilities, we expose it to a variety of different environments to simulate the space environment. So we have to go through a vibration test to simulate our launch environment, because the launch vehicle is very shaky. Then we also have 2 different thermal vacuum tests that test the system in a flight-like configuration to make sure boxes don't get too hot or too cold and everything is operating as designed. So it's a really critical step, and then once we're done with that, we bring the system back into our clean room, do a couple last functional health checks to make sure everything is okay, and then next spring, early next year, we're shipping it to India.
Very exciting. Well, thanks so much, Wendy. We're going to bring Wendy back a little bit later to answer some of your questions, but now we're going to be breaking down the vast communication system that is on NISAE with lead end-to-end systems engineer Richa Sirohi. Thank you so much for being here today,
Yeah,
Richa.
excited to be here. Thanks for having me.
So that's a big title.
Yeah.
Tell us exactly what it is that you do here.
Yeah, so I'm the end-to-end information system engineer on NISAE, and I'm basically the mission plumber. Just like plumbing is a critical part of the infrastructure for any building, so is the data flow. So I think about everything from when a scientist says, this is the data I want, all the way through when that data is archived. So I have to make sure that we can command the spacecraft, that we can collect data correctly, that we can process it on board, downlink it, receive it, and archive it to make it freely available for scientists without having any clogs or any leaks.
I like that. So tell us about your personal connection to ISRO.
Yeah, that's a great question. So my parents are actually Indian immigrants, and they came to this country like many immigrants to give me better opportunities and an education. And I feel really proud that I've been able to take that and work at this incredible place and now contribute to this great Earth science mission that is also in partnership with ISRO and is going to help so many people in India due to its impacts on our understanding of agriculture as well as coastal regions of India.
And tell us what sets NISAR apart. Its communication system is very unique.
Yeah, so there's two big things. First, we utilize ground stations both operated by the Near Space Network, which is operated out of Goddard, as well as ground stations operated by ISRO in India. And so it's very complicated because we're interfacing both with ground stations that we are familiar with as being part of JPL, but also ISRO ground stations. On top of that, it's generating a lot of science data. It's like a tsunami of science data compared to other Earth science missions. It's almost 40 terabits every single day. To give you some perspective, that's like downloading 33 million Word document pages. And if you printed that, that would be 6,500 filing cabinets.
Oh, wow.
It's like if you streamed Netflix for 2.5 months straight. It's a lot of data, so we're excited.
And I'm sure the scientists are excited.
Oh, yes.
As well. And so you've talked about the massive data volume capability. The scientists are just waiting for it. And with all of the things we're hearing on the news about all the flash flooding here in the United States, the record heat in England, the fires in France, how is NISAR going to be able to help take a look at all of these issues?
Yeah, so NISAR is actually doing a polar orbit of Earth every 12 days for about 3 years. That's going to allow us to see on a centimeter level how Earth is changing over a very long period of time. That gives us a really good perspective on how ice shelves are moving, how sea level is rising, how coastal cities are being impacted, how agriculture is changing. It'll inform our climate models, carbon flux models. Basically, that helps us be prepared in the event of disaster responses, how to manage our groundwater, how to manage our agricultural crops and supply chain, how to prepare our cities for rising floods. It's going to be very impactful science. And what's great about it is all that science becomes freely available for anyone to access and use, and will eventually inform environmental policy.
Well, I can see how everyone is getting really excited to get this launched and heading into next year. So thank you so much, Richa, for being with us. We're going to bring Wendy back in here, and now we're going to get to your questions and comments. We've got our social media team that is going to be kicking us off here with Brian on Twitter asking, this antenna configuration looks very different than the large, flat, rigid panels of earlier missions. Can you describe how this new configuration was developed and other engineering advancements that are a part of NISAR?
Right, so I think you're referring to some of our older synthetic aperture radar missions where we use phased array technology. We have a flat panel with individual electronics on each panel where we sear the beam individually. That configuration does not work well for NISAR, and that's because we're sharing this antenna with ISRO. It would be probably prohibitive to launch two phased arrays together. So instead we have a smaller array on the feed of the antenna. That's where we talked about the feed. We have all the electronics behind that, and then they illuminate the reflector together. So the reason why we have this reflector configured is really so we can enable the dual frequency system.
Great. Now, Money Minter on YouTube asks, hey, what is the exact role of ISRO in this NISAR mission?
Yeah, so they're, as Wendy had talked about, are contributing the SR radar, one of the two radars involved in NISAR. What makes it unique is that NISAR is the first time we're having a two-radar Earth science mission. And it's a great partnership because they're also providing the launch vehicle and the launch operations, and they're also providing the ISRO ground stations.
And the spacecraft.
Yeah, you're right. Yeah, and the spacecraft.
They're contributing a lot to this mission, which is why we have the partnership, of course, because it's an expensive mission, and NASA could not do it on its own. So having this partnership is critical.
And being the first Earth satellite that we are in joint partnership with ISRO is really special as well. All right, Drero King on YouTube asks, how is NISAR going to help agricultural production?
You want to go?
Sure, yeah. So it's really helping us understand what best practices farmers can utilize, what crops to rotate to make sure their soil is healthy, how to utilize groundwater resources. It'll inform our water management, so where should we be sending water, how can we prevent from groundwater loss. It'll inform supply chains, so what is working, what areas are a food desert, how can we make our supply chains more robust. So it's everything from water management, farmers, pesticide management, all the way through societal infrastructure and supply chains.
And like you mentioned earlier, and I'm learning along with everybody else at home, so L long, S short. They each look at things differently, but together they really pack a punch.
Right.
All right. Now, our next question comes from Ayush Sabkota on YouTube asking, will NISAR be able to see the amount of water vapor in the atmosphere?
That's not really what NISAR does. It operates at a longer wavelength, so it does not. It sees right through clouds. It doesn't see anything like water vapor. We'll leave that to another mission.
But what's good is it does see right through clouds, and that's extremely beneficial.
Right, so that allows us, instead of looking through water vapor, we have cloud and vapor missions, but this allows us to see through the clouds, so that gives us actually day and night ability to watch and monitor the Earth. It doesn't matter, it doesn't need, cloud cover is not a problem, so we just see right through all of that.
Which is great,
Yeah.
and that's also groundbreaking as
Yes.
well. Okay, next we've got Florian on Facebook asking, what height and where is it going to orbit?
Oh, I'm blanking.
It's around an 800 kilometer orbit.
Okay.
Yeah.
Yeah.
And it is Earth orbiting.
It's an Earth orbit and it's a polar orbit. Yeah.
Great, thank you. Xavier on YouTube asks, does only NASA and ISRO have access to their country's data, or global data is accessible to all countries?
Yeah, that's a great question. So when we downlink at the ISRO stations and at the Near Space Network stations, all that data has to get processed so it's understandable. And it's shared with the entire science team, whether they're from NASA, whether they're from ISRO, and it's put on Earth data for NASA, so it's, accessible for anybody at any academic institution, any personal researcher. There's actually specialists here at JPL who can help you understand that data and help different academic institutions utilize that for research. So it's pretty vast and very accessible.
And there's a lot of early adapter programs that people can get involved in as well to learn more about how this science data can impact whatever research it is that they're doing.
And I'm sure there's more research that will come out of it because of all these early adopters and all of these researchers who get a handle of the data, they find new areas of research as well.
Great. Next question comes from Sandesh Tidake on YouTube asking, which communication technique is used to access this huge data from the satellite?
Yeah, so we have, like we mentioned, multiple ground stations. So every time we do a flyover of a ground station, we'll downlink to that specific site. So we have multiple downlinks a day, especially over this sort of 12-day period that we're mapping Earth. That allows us to collect everything. It's streaming from the internal avionics system. It's our first time utilizing a solid-state recorder, which allows us to manage that volume of science data. Afterwards, it goes through our ground data system, where it, gets accessible and it becomes readable. Otherwise, it's just coming down at ones and zeros, right? So it doesn't make any sense until we put it together on the ground and then make it accessible in our archive. So it's really a multifaceted communication system. We actually have an antenna, which you can't see here on this model, but it'll be right here underneath, and that's how we'll transmit data down.
And you're watching a NISAR live stream right now, so please ask your questions from our experts here. Wendy and Richa are going to be with us for the next 5 to 10 minutes, so make sure you get your questions and comments in there. Our next question comes from Giselle on Facebook asking, I'm a grad student and wanted to know how you both got to be where you are now. What classes did you take, and do you have any advice for students?
Yeah, I love that question. So I actually studied mechanical engineering, but now I do something very different. And that's because, I stayed curious and I asked a lot of questions. I actually found this role at a Society of Women Engineers conference. I got really involved in things I was passionate about and that shined through. And that helped me find the opportunities I have here. And then I found that I got interested in different things and got different opportunities because I just kept asking questions, showing up in meetings and asking for more responsibility. So that's a big part of it. It's not just what class you take, but sort of what piques your interest and how willing you are to pursue that.
And for me, so I've been at JPL like 30 years. So I've been around a while, but I think it's a similar thing. I started electrical engineering. I loved math and science, so that's what I did. And I liked RF and microwave, so I worked up as a RF design engineer, worked my way up to be a system engineer. I spent my whole career at JPL actually in the radar section, so I've been working on radars my whole life. And someone might say, oh, that's boring, it's the same thing. But no, the interesting thing at JPL is I've never worked on anything twice. So it's every mission I've worked on is completely different. I've worked on multiple L-band radar missions, and they're both completely different technologies. And it's just it's exciting working with the teams and the people. And as Rich has said, you branch out from areas of school that you've never even experienced before.
Yeah.
So it's actually very exciting.
And I'm sure, as both of you can attest to as well, there's always a place for you at NASA, whether you're a scientist, an engineer, a communicator, a writer, social media expert. There's really a home for whatever your passion may be, wherever it may be, at NASA or wherever you find your home, as long as you love it, right?
That's right.
Yeah.
Yes. Okay. Paul on Facebook, going back to our questions, asks, for planetary missions, we often see duplicate spacecrafts kept on the ground for troubleshooting issues after launch. Is that done for missions like this as well?
So yeah, I think what you were referring to is a test bed. So we have mission test beds, and absolutely we have multiple types of test beds. We have a radar-only test bed, so if there's any troubleshooting of the radar itself. We have a mission system test bed to deal with the communication and commanding issues and the telemetry issues. So we have a variety of test beds on the ground that are ready to go and needed on orbit.
So just like the Mars rovers, they've got testing machines.
Right.
You guys
don't
have
all the
testing
wheels, but yes, we have a similar kind of technologies and test beds. Yes.
Wonderful. Ayush Sapkota on YouTube asks, how will it look into the ground without getting disturbed by clouds?
Okay, so I'll answer that. So as I mentioned earlier, it's an L-band, and so L-band is 24 centimeter wavelength. So that actually can see, as I mentioned earlier, through the trees right to the ground. And if it's a very dry ground, it can actually penetrate a couple meters below the surface. If it's wet, it probably won't see very far into it, but it is able to tell how much moisture is in the ground by how far it penetrates into the surface. You know, it's been something back on missions back in the shuttle days with a CIRCE mission where they were able to see ancient rivers in the Sahara Desert that were there thousands of years ago that aren't there, and they can do that through what's called ground penetrating radar.
And then the difference between L, which is the long wavelengths, and S, which is the short wavelengths, what kind of things are you going to be able to see with the shorter wavelengths?
So the S-band, if the surface is very dry, it could also do some level of penetration, but its real benefit is looking at the vegetation, at the crops, all the things that, especially, and that's why India is interested in, because that's really their primary mission objective, is to really help their climate and understand all the coastal regions and the land surfaces and all of that. So they look more at the land, and they don't do as much penetration.
Wonderful. Xavier on YouTube asks, how much resolution does NISAE provide?
Yeah, so the imaging swaths are about 240 kilometers and they overlap. So when we're bouncing, we're taking the radar images and we're bouncing it back, those images or the swaths are overlapping. And so that gives us a resolution of almost, we can see changes at a centimeter level, but we definitely have a resolution at 5 to 10 meters.
Right. And so we have two types of resolutions I want to point out too. So we have the 2 to 5 meter resolution is our spatial resolution, but we also use a technique called this repeat pass interferometry. You might have heard people mention. It's an advanced technique where they actually repeat the orbit with 200 meters, and from that they basically kind of do stereo imaging, you could think of it, and that's where they get this sub-centimeter level changes on the Earth. So when they do a repeat, they can actually see very, very minute changes, and that's where they can actually look at earthquakes and the motion of the Earth that you would never even see, with the naked eye, of course. So it's very a lot of resolution at that point.
That's wonderful. Now, Sandy on Twitter asks, what's the coolest thing you've ever worked on so far with this mission?
I'd definitely say the ISRO partnership, like just getting to see how another space agency applies their engineering principles and thinks about the engineering interfaces, and just getting exposure to how other people think can really inform our own creative processes and help us reflect on what we're doing best. And that's just been an incredible aspect of the job, right? Part of it is the sort of diplomatic, intellectual exchange, and I love to be a part of it.
Yeah, I agree with that. I also, because I'm the instrument manager, I'm fascinated by the instrument. It's probably the most complex instrument I've ever worked on, and I've worked on a lot of radars. I mean, the antenna is complex. It is a feat of engineering. The instrument itself, and this is both the L-band and the S-band instrument, it has so much capability. It has ways to have high resolution, wide swath. It has high power. It has very sensitive. So it's just a very exciting mission that and a lot of technology that makes that happen.
Harry Prasad on YouTube asked, does NISAR cover disaster response?
So the data can be utilized to help us understand how to better respond to things like wildfires and rising floods and things like that. And we could potentially see how, areas impacted by certain disasters are able to recover over time. That'll certainly be part of the data set. But it's really more of how we utilize the data to inform environmental policy.
Right, but there is a part of our design that we actually do have a way to change our orbit and be able to respond to disasters quickly. So that is part of our goal. But yes, the science of a long-term societal benefit is what we're working towards. But responding to disasters is definitely something we're working on.
Yeah.
All right, and Connie on Twitter asks, what are you excited for NISAR to show us?
What's your favorite thing?
Well, I'm just excited when we get it on orbit, get that antenna deployed, and get that first image. There's nothing like the first image where you're gonna, it's kind of amazing how quickly they can turn around an image. You were talking about the data volume. They'll be able to, within 24 hours, start producing the first images, and it's really exciting. I think that once that happens, you can see the full capability. You can see it penetrating, you can see the S-band seeing its surfaces. It's just gonna come together, and I think it's gonna really be an exciting mission.
Yeah, I think what's exciting is, we talk a lot about climate change, we talk about environmental impacts, but we can't really solve a problem if we don't understand it. So it's almost like we're diagnosing the issue, and I'm so excited to see that data come back.
Well, I'm so excited for both of you. I know, Wendy, you just got back from India.
I did, yeah.
So thank you for being here, jet lagged and all. And you're both going to be traveling there. So it's a really exciting time as NISAR moves forward. So thank you to both of you for joining us here today.
Thank you.
Well, thanks for having us.
Thank you.
And thank you for all of you at home or wherever you might be right now watching us as well. NISAR continues its journey as it goes into its testing phase and then final integration as it moves to India and launches in India no later than 2023. If you want to follow this mission and get more detailed information, head over to @NASAJPL, @NASA, and @NASA Earth, and follow us on both Instagram, Twitter, and Facebook. At NASA Earth, your home is our mission. Thanks so much for watching.